Okay, so thank you. I think that in the beginning I'll explain what Wslink is. Oh, can you hear me fine? Okay, so Wslink is an interesting piece of malware that we discovered, and all of its samples were protected with an interesting virtual machine. And our motivation to deobfuscate this was to see what is under the hood of this sample. So in the beginning, there weren't any clear artifacts about which would suggest what the virtual machine was. But after the publication of our paper, several researchers reached out to us and told us that this is something which really looks like code virtualizer, which is basically like the virtual machine used in Temida, and we afterwards verified and confirmed it. So we'll talk about code virtualizer, and it should be fine because it wasn't publicly described before, as far as I know. So I think that now I'll tell something about me. So my name is Vladislav Hrčka, and I've been working as a malware researcher at ESET since 2017, and I've been focusing on reverse engineering challenging malware samples. And I'm currently also studying computer science at the Comenius University in Bratislava. And that's everything about me. So what this presentation look like? So in the beginning, we will look into what virtual machine obfuscation looks like in general, and provide a quick introduction into symbolic execution. And we will afterwards discuss what the internals of the VM look like, and then describe approach how we dealt with the obfuscation and demonstrate our approach. And I'll also say that we weren't motivated to fully deobfuscate this machine because subsequently starting our analysis, we discovered a non-obfuscated sample. So we will eventually just deobfuscate several chunks of bytecode and compare it against the non-obfuscated code. So what do process VMs work like? So they work just like standard machines. They use some bytecode that works like machine code that consists of instructions that have opcodes and operands. And we can see in the left side what VM can look like. There's this interpreter that is basically a dispatcher that takes opcode from the bytecode, and based on that decide what handler which defines its functionality will be executed. And for example, the first one fetches 2 operands from the bytecode and performs an operation, and then returns control back to the dispatcher, and it sequentially continues. But these dispatchers can look differently, and this is called direct dispatching, but there's another technique called threading dispatching, which basically do not have a direct dispatcher, but each handler at the end of the execution calls another one. And now how can one use this construct to obfuscate code? So if we look at the function one, it's an example, and one can translate the original code of the function to a bytecode or to a custom bytecode of a virtual machine, and rewrite the original code with call to this machine's interpreter, and actually in contrast to standard virtual machines, one needs to perform like some context switch here, because we are virtualizing just a single function. So we need to like choose the respective bytecode like for the function, for example, based on like caller's address, and then switch from like native context to the virtual one, because like standard registers like RAX need to be mapped to, for example, their virtual variants. And when this context switch is performed, we can like execute the interpreter that executes the function. And when it's finished, we need to map the virtual context back to the native one and continue in execution. So now symbolic execution, it basically expresses code in like form of mathematical formulas, and registers and memory are treated as symbolic values. And we do not want to perform like some code coverage, but we just want to see some summary of code effects on these values. For example, in the left side, we can see some original assembly code, and on the right side, results of the symbolic execution. And we will use framework miasm in particular. So in the right side, we can see, for example, that the curly brackets perform like some compose operation, and we see that the EAX register will contain at the end of the block like composition of the referenced value from ESI register. Like we can see that the @ sign means that the code will perform like the reference, in this case like of a 16-bit value, and we can see that it takes the 16 bits like in the curly brackets, and the upper half is basically the EBX register. And we can also see that the return address right away is like the reference of EDX XOR of 123. And now, how is it useful? So in miasm, the symbolic execution engine performs automatically like some optimization rules. So when we like replace, for example, the EDX register with value 96, and we say that in memory the 96 value contains this feed value, we can again evaluate the basic block and get the result which are on the right side, and we can right away see, for example, that the return value should be the FFCE value. And actually we can see that there's some IRDST, and it actually stands for intermediate representation destination, which is like instruction pointer in the IR. And now this is like the end of the introduction, so let's jump straight to the virtual machine. So if we open a sample virtualized with this machine, we can see that this start address contains this call to a function that we identify as VM entry, and the remaining code behind this looks basically like gibberish, and there are actually like 7 calls to this function recognized by IDAS, so that means that there are at least 7 virtualized functions. And now, before we discuss what this VM entry function does, we can have a look at this junk code. And actually the virtual machine uses this junk code in many places, and on the right side that's IDAS attempt to like decompile this code, and on the left side we can see that the miasm's symbolic execution was actually able to simplify the code much better, and we can see right away like what the basic blocks does. So let's look at the VM entry, and we actually like analyzed all these components, and we needed to like remove the junk code and analyze it using the symbolic execution to know what happens. So the VM entry unpacks the VM, and it's actually in a separate section, and when the VM is unpacked once, it just directly executes it and then decides what VM preinit will be executed based on the caller's address. And this VM preinit actually contains, like each of them, a hard-coded address of a bytecode, and apart from that stores CPU flags and calls. All of them call one common VM init that saves like rest of the native context on stack, and it additionally contains some synchronizations because the virtual context is like in the section with the VM, and it's only one, so all the threads need to somehow synchronize not to override it. So apart from that, it actually relocates its internal constructs and executes first virtual instruction, but there's this issue that each of these virtual instructions, there's 45 of them, is virtualized again, and we can see that there's similar like VM2 preinit and VM2 init, and now there's even more than 1,000 virtual instructions, and the reason is basically that all of them are duplicated, and just for example, they're on like average had like 170 native instructions, and the instructions in the third one are around 55,000. So it uses like direct threading, and each virtual instruction can like either execute another one, leave the VM, or execute another VM preinit. We'll now look at virtual instructions of the second machine, because the first ones are just virtualized and we wouldn't see anything at this point. So what happens here is that the destination address is set to this pretty long expression, but we know that RBP init basically contains a pointer to the virtual context, and A4 is offset like of a table of the instructions, and our BP init plus 28 contains like the pointer to the bytecode, which means that this basically decides based on the bytecode what next instruction will be executed. And then we can see in the next line that the bytecode pointer is like, which is actually like virtual program counter is increased, and another register is set to 0. And next two virtual instructions are not that interesting anymore, but we can see that in the second one several like virtual registers that are like reference relatively to the virtual context are set to 0, and the third one just stores RSP in a defined register based on bytecode. Now the fourth one is interesting. This one is basically the first one that used like multiple basic blocks. And if we look at the summary of the first block, it contains this weird expression that basically encodes operands and the instruction that the register, virtual register that should be used. And actually these registers were used in the second instruction, and they were set to 0 there, so we can basically simplify this expression, and if we like set them to concrete values, we would be able to determine what register is being accessed. And this is actually called rolling decryption. It was mentioned in the blog post about VM Protect. So if I manage to lose you now, or pay attention now, it should be interesting in the following slides. So if we look at the first block and see this expression, we can like apply the values of the rolling decryption registers and get a bit simplified expression. But now we see that there's still this reference to the virtual program counter, and if we actually apply operands that are known, we can simplify the expression even more. So this is the final simplified expression, and we can actually see that it stores like the value which is on the top of the stack in a register, and subsequently increases another register by 8, and then just increases the virtual program counter, which means that this is basically pop. And now if we look at the summary, we want to deobfuscate the bytecode in the following way, that we will just create like control flow graph out of the summaries to see what the bytecode actually does. And we'll do that like that we will treat these registers for rolling decryption as concrete values, and additionally values that are relative to the bytecode pointer, which means basically that all the operands, and we will preserve the values of the decryption registers between the blocks. So now this is a result of one of the deobfuscated instructions of the first VM, and basically we can see that there's the 0 assignment in the beginning, and then we basically ignore the registers for obfuscation, so the other block is empty. Then we store the RSP, and then we can see a series of pop instructions, and basically this is the reason, because earlier I mentioned that vminit stored the native context on stack, so now we are like mapping it to the virtual registers. And what does outro look like? We basically need to like perform the context switch again, back from virtual context to the native one, and we can see that the values are pushed onto the stack and subsequently again like popped onto the native registers, and the next instruction basically is determined by one of the registers, which means that it sort of jumped to one of the registers. And now we can take a look at the initially executed virtual instructions of the first VM that was basically now deobfuscated, and the first 3 are actually the same ones as in the previous VM, and the 4th one is interesting. We can see that this is just a part of the instruction, it's very big, and we expected a simple pop operation like before. So what's the problem? Actually it performs instruction merging, so there's like multiple operations, and operands decide which instruction is executed. So we now like zoomed in on part of the instruction, and we can see that here basically happens push, and at another place a sort of pop. So how can we again simplify this? We can apply the values from the bytecode and decide what path is taken and what operation we actually performed. So now we will do actually the same as in the previous machine, and we will additionally make like the entire VM2 concrete, because we know what memory range belongs to it, because it's like in the separate section, and we will additionally ignore assignments to the second VM to like see only what happens in the first one. So now when we attempted to like perform the deobfuscation again, we stumbled upon these results, which basically weren't expected, because we wanted a simple series of pop instructions. But if we zoom at one of the blocks, we can see that there's, for example, this comparison of RBP init, that is basically address of the virtual context that is known, and we can apply this value to like simplify the branches and get a simplified graph. So does this approach work? We can in the first place see some statistics. So in the beginning we had like in the second VM 17,000, around 17,000 native instructions per bytecode, and we were able to simplify it to like 109 or 300 instructions in the intermediate representation in like 10 seconds. And in the case of the first one, we needed to like deobfuscate both VMs at once, so we needed to process like 3.5 million native instructions and reduce it to like roughly 200 in 380 seconds. And now we can compare the results of the like obfuscated function in the left and the original non-obfuscated sample in the right. We can see that the prologue of the function is actually the same, but the next line is a bit different. It doesn't contain a reference, but if we look at the resulting deobfuscated control flow graph, we can see that the reference is actually here. And if we like simplify this to sort of pseudo instructions, we can see that it actually performs the same thing as the original sample. And now we can go on and compare the rest of the function, or the first part of the function. So here we can see that actually it uses this virtual register at offset 80, and it is actually like it contains the base address of the code, so it can perform like relocations dynamically. So we can see that it adds this constant 3808, which basically contains a structure recognized by IDA as service status, and it's basically the same as in the original sample. Both contain this loop. We can see it like right away, and then it decreases a register and sets value to 0, just like the original code. We can go on. We can see here again the register with base address that basically contains address of the handler proc in the right picture, but it wasn't recognized by IDA this time. It's just as a function. And then there's this simple assignment. And I forgot to mention that we actually perform some additional optimization techniques. So we are not like explaining all the instructions, because they are just like not that interesting and they could have been removed. And now basically this bytecode ends with this call, and we can see that it sets this register to the address of this API, And at the end of the block, we can see that it actually jumps to the register, so it performs that call like this. And the return address of the call is set like before, and it is set to another VM preinit, which means that when the API call is finished, another bytecode is executed. And what are the limitations of this approach? Basically the same as in symbolic execution. We cannot process instructions that contain unbounded loops, and we need to process these instructions by some other means. And what is the takeaway? We can use symbolic execution to virtualize some advanced unknown VMs in a reasonable time, if we treat the right values as concrete. And by advanced, we mean VMs that merge or duplicate handlers and use junk code. And the right values are basically operands and the virtual registers used for rolling decryption. So if you're interested in the full paper or source code, you can find it at these links. So thank you. Do you have any questions?
Thank you, very nice work. I asked something that probably I didn't get it. Can you say again what was the link between the first VM and the second VM? I mean, let me explain. It's like after you executed an opcode of the first VM, then there was another VM unpacking the opcode, or did I misunderstand?
Yeah, basically, when the first virtual instruction was executed, we found another, I mentioned, this VM preinit that contain hard-coded address of a bytecode that should be executed, and it stored additionally the CPU flags, and then executed the VM init, which is common for all the VM preinits, and the VM init based on the supplied parameters additionally pushed rest of the context to the stack, and then executed the first version. I didn't mention that apart from the bytecode address, it actually pushed offset of an instruction which is supposed to be executed first, and based on this offset, the VM init fetched the address of the first instruction from the table and executed it, and set the bytecode to the virtual register that contains the VM or the program counter. Did I answer your question?
Yep.
Thank
More
you.
or less, I think that I understood. Thank you.
Thank you.
Hi, thank you for the talk. Can you share some details about how you found the unobfuscated sample?
Well, it popped up on a VirusTotal based on some Yara rules, but it actually is not that interesting for this talk, I think. Is it?
It's interesting for me, but thanks. I'll
Well, basically
later.
Yara rules on VirusTotal.
Okay, thank you.
And it was one day uploaded, and we found it.
Thanks.
Any other? Oh.
So similar to like the question before about like where did you find it? Did you also test this on many samples? Did you get like a large statistical?
Could you please speak up or?
Oh, okay. Did you test this on a lot of different samples besides the one that you demonstrated here? And did you get like statistical results about how well it worked?
I executed it on like several bytecodes in the sample, in the one sample.
Yeah. Another question. You mentioned about that you found a link to Temida. Was that right? Can you share some details about that?
Oh, can I what?
Share some details about that.
Yeah, well, basically some researchers pointed out that it's very similar to that, and afterwards I made some Yara rules for the packer and collected some samples on VirusTotal, and when I collected them, they usually contain sections vlizar, which is very common for code virtualizer used by Temida, and well, that's it. And then I looked at the samples and I saw that the packer is the same, and when I unpacked some of them, the constructs were also like the same, but not in all cases, because code virtualizer uses like a number of VMs, so there were some differences, but not as significant.
Thank you for a very nice presentation. What are your thoughts on where to take this next? Is the first question. Where do you want to take this next? Like, what's your ambition to do next? And the second part of the question is, do you have any favorite books, references, or trainings on how to bring colleagues up to speed on this quickly?
I don't really know what I'll be doing next, but I think that actually there's a number of blogs from the miasm authors, and actually I probably forgot to mention that, but they deobfuscated like Zeus VM, and they used like also this symbolic execution, but they didn't make like the operands and operands concrete, and the VM didn't have like duplicated operand opcodes and merge instructions, so didn't have to like deal with the rolling decryption. So I would, in the first place, look at their work, and then, as far as I know, team has some great materials you can look at. It's very well explained there.